source which is parallel to the resistor can be replaced by a potential source connected to the resistor in series. In this case, their resistance is exactly the same. Just we have to figure out, given the Vs, what would be Is, or given the current, what would be Vs.
Temenin ortamında da böyle mi oluyor?
Aynen. Yani yaptığın şey zaten birini bulduktan sonra diğerini geçiyor.
Norton soldaki bir
So the value between the relation between the current and the potential is this one. So once you have one of them, you can change it to the other one. And they were right. This is basically what we have Thevenin and Norton circuits. Remember what we do with the Thevenin equivalent and Norton equivalent circuit? The idea is sometimes the circuits are very complicated, which means you might have a box here, which is representing many resistor potential source connected in different way. But at the end, if the problem is only interested with when I connect a load across the nodes between A and B, and if I ask you what would be the value if it changed to 5 ohm, 10 ohm, 15 ohm, you don't have to repeat that question again and again. Once you can find the representation of this box, you can easily solve that question. The idea behind that is figuring out what would be the equivalent of this complicated circuit, which means I can represent this circuit by Thevenin equivalent, which means I should have a resistor and potential source. That's basically my Thevenin equivalent of the actual circuit, but obviously you are supposed to calculate what this potential source, what that resistance is. That's the part that you have to work anyway. The idea is you can get the Thevenin equivalent if in the actual circuit, if you calculate what is the open circuit potential, and you can get Thevenin resistance by Thevenin potential divided by the short circuit current. Again, this is from the actual circuit. This is from the actual circuit. So by analyzing that actual circuit, we are supposed to calculate what is the open circuit potential and short circuit current, so that we can also calculate what is the Thevenin resistance. And remember, we have an alternative way to calculate this one. If all of your sources in your actual design are independent sources, then you can zero all of them, like this one. Let's say this is my circuit, and I would like to figure out Thevenin equivalent of this circuit. So which means this one can be represented by that means, again, the idea behind it is, since it's exactly the same circuit, if I put a load here, and if I put a load here, potential across this and potential across that one should be exactly the same. That's why we are doing Thevenin equivalent. I don't have to worry about this circuit every time I need to change something. Once I have the simple version of the complicated circuit, I can use it. The idea is, again, first I have to calculate Thevenin potential, which means from the actual circuit, I have to calculate what is the open circuit potential. Open circuit means I'm interested between the points A and B, right? It is this. Nothing connected here. And I am trying to get the open circuit potential between A and B. I'm not going to solve this circuit since it's might not be realistic, but remember that's how we do it. This open circuit potential will be equal to Thevenin potential of our circuit. Then I might also calculate short circuit current, which means I short circuited between A and B, and then figure out what this value is. Again, we have to analyze this system and then figure out what is the short circuit current, so that I can calculate Thevenin equivalent, which is going to be open circuit potential divided by short circuit current. But let's discuss this alternative approach to calculate Thevenin resistance. Independent of calculating short circuit current, I can still calculate Thevenin equivalent. The idea was, when I look from this perspective, what I see, that's what we are trying to calculate, but we have to zero all the independent sources in our case. So we have a current source. How do we zero it? I don't want to have any current, right? That's what zero current source means. How do we zero this one? It's open circuit. I have a potential source here. How do we zero it? Short circuit. Now, when I look from this perspective, and this is, let's call R4. What is the equivalent resistance? This is open circuit. I have R1, R2, R3, R4. When I look from here, what do I see? Who have the answer, brother? You are correct. So, when I look from this side, what I see for the rest of the circuit, what is the equivalent resistance that I see between A and B? And how they are connected. So, since this is open circuit, I don't care what is R1 and R2, right? Because there is no current flowing through them. So, it's not going to change my circuit. Only thing is left, these two which are going to be parallel to each other. So, in this circuit, our Thevenin resistance would be this one. Once you have it, by using the source transformation, if you would like to change it, you can also change the Norton equivalent of this circuit. Because basically, Norton equivalent and Thevenin equivalent are same system by using source transformation.
Hocam bir şey sorabilir miyim? But if there was like a diamond source, onları da zero yapıyor
We cannot zero them.
Okay.
She is right. We also discussed that if we have dependent source, we cannot zero them. But what we are supposed to do for that case, actually let's find an example so that I will talk about an actual. So if this is your circuit, let's say this one, and the problem is asking you to calculate Thevenin equivalent or Norton equivalent system, the logic is the same. How you get the Thevenin equivalent is calculating open circuit potential between these 2 points. So again, you have to repeat this analysis. Depending on your circuit, sometimes in this case the question is solving this problem with mesh current analysis. So once you have this, but one thing that you have to be careful when you have this circuit. Remember, this A and B are not connected to each other. So when you calculate or analyze this system, what is the potential here? If you compare this point to that point, what would be the potential here? It would be exactly the same thing, right? Because remember, this is open circuit, which means there is no current flowing through 2 ohm resistance. That means the potential this point and potential that point is exactly the same. This is B, this is B. This is A, this is A. Which means actually, at the end, open circuit potential you are supposed to calculate will be potential across 6 ohm resistance. That's how we are supposed to solve open circuit potential in this question. And in the second part, the problem is asking this. So, which method it uses? It's using the test current method. So, what the problem does, to calculate this RThevenin. In this problem, we have independent sources. So, as you can see, what happened, this is independent, so still you can zero it. So that's why we don't have that current source anymore. Nothing else. We cannot neglect this one. It is still there. What happens now? It put just a test circuit. This is not actually there. But the problem tells you that if I connect here a potential source between A and B, and I know the value of this potential, that's something that I choose. You can use 100, 200, doesn't matter. Once you have this potential, what you are supposed to figure out? Current here. Because this potential divided by the current, what will potential divided by the current, what will be the answer? So if you have this potential and then calculated the current, potential divided current would give you equivalent resistance of the system, right? Because this current is depending on the rest of the circuit, what is connected between A and B. So if you know this potential and if you calculate what's I0, this divided by I0 is going to give you Thevenin resistance of the circuit. That's how you have to do it if you have dependent sources. Or still you can use the calculate the short circuit current, solve it, and then get the Thevenin resistance. But those are, let's say, doable, but there are many analyses you have to perform to solve those problems. So that's why I am not gonna ask these questions, because it will take time. So don't worry about it. But still you have to know, if I ask you if this is the circuit, and if I ask you what is 1 volt, 1 V divided by I0 is, you have to know the answer. That's the thing that I am asking. Yes, analysis approach, you can do it or you cannot do it. It can take a while. But the main idea is, do you know what V0 divided by I0 will provide you? That's what I'm interested in. Did you understand that part or not? That's the important part for me. So, we have discussed the Thevenin equivalent, Norton equivalent. The last thing is superposition principle and maximum power. What was the superposition principle? No, it's not the last thing. We didn't talk about the conductor and capacitor. Inductor and capacitor. Anyway, what was the superposition principle? How do we apply superposition principle? How do we use it?
If there is, for example, 3 current or voltage potential sources, we are just using one and neglecting others. We calculate for each of them and when we topladığımızda hepsini gerçeğine eşit olmuş oluyor.
He is right. The idea of superposition principle. Most of the time in an electrical circuit, you will have more than one source. It might be voltage source or current source. The idea is, if you are trying to, let's say, calculate potential across this 2 ohm resistance, this potential source and this potential source both affect that number. So superposition principle tells you that if you neglect this one and measure the effect of this potential source, by the way, both of them should be independent anyway. Let's put actually an actual circuit again so that we are not going to have issues. Like this one. So in this case, they are all independent. So if you are trying to calculate what is the potential across this 3 ohm resistance, it's really dependent on this current, right? So you are supposed to find the current. The superposition principle tells you that this current is affected by this source, and that source. So individually, if I calculate what would be the effect of, let's say, the value of this current if there was only this potential source, and solve the problem. If this would be the only potential source, solve the value of the current. And if this would be the only current source in your system, solve the value of the I. So I is going to be summation of all those three numbers. Again, this is not really most efficient way of solving these problems, because most of the time there are going to be much more simple analysis approach, but at least you have to know what superposition principle tells you. We discussed source transformation, maximum power. Remember, we have discussed that. If we have a load and if you are trying to figure out what will be the maximum power that you can deliver to that load, then the value of this load resistor should be equal to Thevenin resistance. That's the thing, which means if we have any maximum power problem, we are supposed to solve actually Thevenin equivalent of that circuit, so that you can get this value and you can get that value, so that you can calculate what is the maximum power of that system. You don't have the chapter 5 because we are not discussing amplifier in this course. Then we are coming to the chapter 6. Remember, these are capacitor and inductor. Just quickly, I would like to remind you the importance of capacitor and inductor in our approach. Then I will talk about the last year's midterm exam. So remember, capacitors are conductor plates, mostly filled by dielectric materials, and once you give potential difference between them, there is going to be charge accumulated. So, and the capacitance value gives you, given the potential difference, how much charge you can collect. So you can give it potential based on the physical value of that capacitor. So what was the material used? What are the dimensions of those plates? It will give you how much charge it can collect. Remember, this is constant. It cannot change because it only depends on the physical design of the capacitor. So if we increase the potential, it will collect more charge, but obviously there are going to be always a maximum level that you can reach. Once, and this is not suddenly happening, so you have to increase potential difference small, let's say, what I'm trying to say, you cannot just in a second you can do it. Instantaneously you cannot charge the capacitor. It will depend on the time. So actually how this is feeling is depending on the time. How much you provided this potential difference to that capacitor will tell you how much actually charge collected by that capacitor. But once it's reached the maximum level, it means you cannot put any more charge on it. Remember, current is motion of the charges. If you are not providing any more charges, which means the charges are not moving anymore. So if capacitor is fully charged, or you can say that you waited long enough, or you can say that you reach DC steady state. All of them referring to the same thing. At this instant, the current through capacitor will be what? Current through capacitor, when you reach DC steady state,
It will be zero.
it will be zero. That's the thing that you have to know. But remember, that doesn't mean that you don't have any potential. You have, because you already give charge to that capacitor. Since it's charged, there's a potential across that one. So you cannot neglect that one. But the problem is, if this is your system, I said that I waited long enough. The system reached steady state level. And if I am asking you, what is the current flowing through the capacitor, what would be the answer? Zero. If I ask you, what is the potential across the capacitor, what would be the answer?
Same as our one.
That's the thing that you have to know. This node and that node is same, right? This node and that node is also same, which means they are parallel connected. What do we know about parallel connection? Potential difference should be always same, right? So that's why, if this is fully charged, and if I am trying to measure potential across this capacitor, it should be exactly potential across R1. How am I going to get potential across R1?
Voltage division.
You can use voltage division. You can calculate current, then multiply current by I1. What you are interested is right now, since there is no current flowing through this capacitor, this is your single loop where the current is flowing, right? Because if I was not asking at DC steady state, there would be also current here. So the question would be completely different. But once we reach the DC steady state, since there is not going to be current here, this is going to be the loop that the current is following, which means this delta V will be shared by R1 and R2, compared with the value of their resistance. And one thing that you have to know, say QC times delta VC. Like that's the current across capacitor. And you should also know how to calculate energy stored by a capacitor. That's how you calculate energy stored by capacitor.
Formülleri vereceğim tabii.
Formülleri vereceğim.
Ne kadarını vereceksiniz? Vermeyecekleriniz de olacak.
Şimdi
Tamam,
şeyi yazmayacağım
vermezsiniz.
size. Node voltage method nasıl apply edilir yazmayacağım. I am not going to write you how node voltage method apply because it's just application of KCL. So you have to know, I can write what KCL is, that's okay, but I am not going to write what would be the node voltage method, or for the mesh current, what I am supposed to write. Should I give you a circuit and then write the equations? So you have to know that mesh current is using KVL. And I'm going to write what KVL does. But other than that, I can give you the delta Y conversion, Y to delta conversion. I can give you what power is. I can give you what capacitance is, what current is. I'm not sure about the current though. Anyway, I will give general equations, but I am not going to talk about analysis method because that's your responsibility. That's you are supposed to know. This is the inductor. There is current flowing through that inductor. Actually, if I would like to measure potential across inductor, that depends on the, again, physical properties of it and derivative of the current flowing through this inductor. That means if this is zero, potential across inductor is zero, right? But remember, this zero doesn't mean that you don't have current. You have current, just you have a constant current. That's the thing you're supposed to know. So, when you reach DC steady state, that means your current is not changing with respect to time anymore. What will be the potential across inductor? Zero. But current is not zero. So how you're going to represent this in a DC steady state? Short circuit. That's the only thing that you have to remember. That's how you're going to analyze those systems. So DC steady state, inductor, changed by short circuit. And how do we calculate energy stored by inductor? Is 1/2 L IL squared. So current flowing through it is what you are supposed to calculate. And in the quizzes, what I have given you, many inductor, they were connected parallel and resistor, and we are supposed to calculate what is the equivalent. Let's do that and see how long it takes for this.
Hocam ya ben az önce quizde bunu soruyu yazarken bununla çözdüm.
Neyle çözün?
Yani induktördeki nasıl serisine bağlandığında 1/, eşek.
Rezistörle aynı hareket ediyor.
Conductor tam tersi. Resistor tam tersi. Bunun ayrısı.
Ama 1/, hocam seride yaptığımızda şey yapmıyor muydu?
Aynı dersi görüşürüz.
20 çıkacak ya, cevap yok.
How long it took for me to draw it? How long?
I'm not a teacher.
You're just drawing something which is not. I didn't draw it nicely, so it shouldn't take 2 minutes to draw this circuit. Anyway, so these are inductor.
30 saniye sürdü. 20
Evet
değil
hocam,
ya, 20
yapamadık
çıkacak.
ya.
30 saniye çıkacak.
Normalde
Geçen hafta deyince
Let's
tamam oldu
just
gitti.
discuss. Stop. So they are since connected in series, and since their potential is really depending on the current, and since when they are connected in series they share the same current, this is like exactly like resistance, right? So 20, 12, 20 and 5. 20 multiplied by 5 divided by, so 4.
Hocam
6 and 12.
4.
8, 8, 4. How long it took?
hocam zaten
You spent more than 10 minutes to solve this question. How long it took? Less than 1 minute.
30 saniye.
That's why you have issue. I don't know what your issue is, but less than a minute. Not complicated calculation. You didn't need any calculator, did you? Think about it.
Can you say the part after the addition again? Can you say the last part?
This becomes 4, this becomes 4, connected in series, which is 8. 8 and 8 parallel, which is 4. 6 plus 4 plus 10 is 20. Anyway,